Okay, so I left this on the board at the end of the last class and go through the mechanism. What I just handed out to you is this flowchart that is found in the Chapter 7 module called Substitution and Elimination Flowchart. So like I've said a few times, the trickiest thing about this chapter isn't so much any of the reactions by themselves. It's that there are 4, and if you count this one, basically 5 different reaction types that can happen, all with sort of the same looking reagents, right? You're going to have a base and a nucleophile. You're going to have a compound that's got a leaving group on an sp3 carbon. If you have all that, you can have any of these substitution, elimination, rearrangement reactions. Okay, so this flowchart is kind of designed to, look at that. All right. So the flowchart is designed to take you through that and give you an idea of what the most likely reaction is. All right, so like I said, if you've got a reaction that could be SN2 or E2, like if you've got a set of reagents and you're like, oh, this could be SN2 or E2, this flowchart will not definitively tell you which it is. It'll tell you which one you should predict. And I don't want to harp on this too much. Like right now, you're in a class, I'm grading your assignment, I ask you questions, you have to write down answers. I give a grade to that. That grade's important to you. Right? That's all understandable. But this is a model, right? This is based on, there's some theory, there's some empiricism based on what we've observed. And that's a lot of what you get in science classes. And this is really what I'm saying is, just as you look at science in the world, there's all this stuff we know that we've learned. But anytime we build a model, like we have to make assumptions, and there's always some uncertainty. And so if you get to the end of this and you're like, this should be an E2 reaction. If you go in the lab and you pour the chemicals together, it may very well turn out that E2 is the major product, but it might be 52%, and SN2 is 40%, and SN1 is like 3%, or something like that, okay? So you can have kind of all of them operate. You can even occasionally have them like just go against this. So I just want to emphasize, this is a way to predict a product. I'm going to ask you to do that according to these rules. But when you go in the lab, things might not work out exactly that way. Okay, and this happens all the time. And I think probably before we begin our science education, we have a more intuitive understanding of that, right? That if I think about sports, I don't like to make too many sports analogies because not everybody's into it, but at the beginning of the NCAA tournament, everybody sort of predicts who's going to win. And honestly, in a regular season, we have a pretty good idea who's better than who. And yet, on one game, somebody, any given game, somebody unexpected can win. There's always uncertainty, even when we think we really know stuff. So anyway, that's your big picture lesson for the day. Like I said, for the next 3 weeks, what you're focused on is giving me the answer I'm expecting. But I do want you to keep in mind that sometimes the answer might be all these might happen, or 3 of these reactions might happen. Okay, so this mechanism, first of all. So let's use the flowchart first of all. And it's a flowchart. It's not maybe it's designed by me, so the art is not terribly good. But we're going to start up in the upper left. Is there a leaving group present? So in this reaction, is there a leaving group? What is the leaving group? Chloride. All right, if there isn't a leaving group, I mean, this sounds kind of subtle, or simple. If there's no leaving group, you cannot do an SN1 or 2 reaction. You can't do an E1 or 2 reaction. So there is a leaving group. Good, we can go to the right. Are there beta protons to the leaving group? Yeah, okay. So that's a little less obvious. The leaving group is there. The leaving group is always bonded to the alpha carbon. The carbon the leaving group's bonded to in this section is the alpha carbon. And then any carbon bonded to the alpha carbon is a beta carbon. So there could be 3 beta carbons. Here there's 2. All right. If this one was the only beta carbon, there would not be any beta hydrogens, right? The beta carbon there has 3 carbons on it, so there's no hydrogen there. But we also have a beta carbon down here, and that's got hydrogens on it. So if you were just looking at this, the way to use the flowchart, we're going to leave the flowchart for a couple of minutes here. You've got a leaving group, so substitution and elimination is possible. You've got beta hydrogens, so elimination is possible. So we can kind of do all 4 of these reactions. Now, in this case, something else has happened. I know you've had a chance to think about it, but just look at the bonds. What's connected to what? Think about that for about 30 seconds. Has anything changed there? My phone froze. All right. So, as you're looking at this, the carbon skeleton has changed or rearranged. We have the same number. We have 6 carbons in the ring, 7, 8, 6, 7, 8. But in the starting material, in the reactant, we've got 2 methyls on 1 carbon. Those 2 methyls are now on different carbons in the product. Okay, so stuff is rearranged. We've lost the leaving group. Okay, so this is either going to be an elimination or a substitution. The leaving group leaves. On the right, I've drawn 2 products here. We've got one that's an alkene. That's going to be an elimination product, right? Leaving group leaves. We get an alkene that's going to be an elimination of some sort. And here, leaving group leaves, and another group comes in, so that's a substitution. But you've got the big thing to figure out here is how do those 2 methyls split up? So we've got a leaving group. Do we have a strong acid or base? All right, we do not. So as we'll talk, when we go through the flowchart proper on some other reactions, if you have a strong base or a good nucleophile, you're typically going to see an SN2 or an E2 reaction. If you don't have a strong base or a good nucleophile, you're typically going to see SN1 or E1. The first step of an SN2 reaction, of an SN1 reaction or an E1 is for the leaving group to leave. All right, so the leaving group leaves, and this gives a carbocation. And chloride. Right? This is the reverse of the last step of electrophilic addition of HCl. All right, now just a reminder about carbocations. So that positively charged carbon is trigonal planar. It's sp2 hybridized. It's bonded to 3 things. If it's sp2, it's got a vacant p orbital. So it's got a vacant lobe above, a vacant lobe below. It's flat. You should remember carbocations are more stable. Tertiary, secondary. That's a really big. Methyl cations effectively don't form. And the reason for this is there's always stabilization from bonding electrons. The more bonding electrons you have adjacent to the positively charged carbon, the more stable it is, right? And we show this bonding pair of electrons can donate electron density into that vacant orbital. That stabilizes the vacant orbital. The other thing it does, though, is it's forming a bond between that H and the positive carbon. Okay, if you take what I've just drawn to an extreme, right, this H could just move to here and leave a positive charge there. So don't think about that as a stabilization. Think about that actually as a reaction. Right? If that H moves all the way over to the positive carbon, you're left, the carbon the H left becomes a positive carbon. And then you would have, right, this positive carbon would have this lobe, and that H could donate electron back there. This winds up being an equilibrium process. And where you're going to end up is at the most stable cation. All right, so a really common reaction for carbocations to do is to rearrange. And they rearrange in such a way as to make the most stable cation. So you remember when we did the addition of HX to an alkene, Markovnikov's rule says we're going to make the more stable carbocation. And so here, this is a secondary cation. This methyl group will take the place of the H, either of these methyl groups, and it will move to the carbocation there. Now, where's the positive charge? So I've drawn the carbon skeleton. There's a positive charge there. Take 10, 15 seconds to consider where it is. Question, or are you going to tell me?
I'll ask the question after they.
Okay. All right. So on the secondary cation, the carbon I've got my finger on, how many hydrogens are there? There's one. Okay, let me draw that in, because that might make it a little easier to see. All right, so the methyl's going to move there. That H is not going anywhere. It doesn't leave, it doesn't move, it just sits there. So now there's also an H here. The carbon that loses the methyl is going to become positive. All right, so does that clear it up, or do you have a question?
So if we're going about most stable carbon, why doesn't the methyl group stay on the previous one?
Well, okay, so this is now a tertiary cation here. Right? The carbocation's tertiary on the right, it's secondary on the left. So the structure on the right is a lot more stable.
Even though the one on the left has a tertiary carbon?
It's, when I say it's tertiary or secondary, I mean the carbon that's positively charged. So that's a secondary cation right there. That carbon's bonded to two carbons. Right? So yeah, I mean having a neutral tertiary carbon is no better or worse than a secondary neutral yet. So you're just focusing on the carbon that's positive. All right, and so in this case, this equilibrium very much favors the right. And this is, I mean, really to predict. When I ask you guys a mechanism question, I'm not asking you to predict anything, right? I'm telling you, if I mix these chemicals together and I got these products, right? I'm not asking you to predict the products. I'm asking you to tell me how those products formed. If I just given you the reagents and said what product forms, one, I haven't given you any conditions. Without temperature, you're not going to be able to differentiate elimination and substitution. So if you'd drawn one of those two, I'd be fine. The other thing is, in reality, like I said at the opening, does something happen? Typically, migrations like this happen pretty often. And that's the rule I'm going to tell you to learn. But again, this will depend a lot on temperature and concentration and all that sort of stuff, right? At low temperature, at at high concentrations, we might actually see E1 and SN1 of this cation, no migration. higher temperature, more dilute conditions, we're going to see more migration. In reality, we probably see elimination and substitution from here. We see elimination and substitution from here. And if you haven't noticed, the substitution product over here can exist as a pair of diastereomers, right? The two methyls can be cis or trans. We'll get both of those. So two kind of general rules. The first one first. How's that? All right. Like I said, actually predicting this, there's a whole lot of variables. As a general rule, the way to bet is if the cation can rearrange to make a more stable cation, it does. All right? So secondary cation going to tertiary, primary cation going to secondary, non-resonance stabilized cation going to a resonance stabilized cation, all those are going to happen. And so if I asked you to predict a product, I'd expect you to predict that. So the other rule, and this is really here I'm probably talking more to the future chemists. Everybody puts their pen down. It's rude. So reactions that go through carbocations tend to be really messy. All right, the carbocation is a very high energy intermediate. It's quite unstable. And like I said, just going through here, every step you add to a mechanism tends to add more products, right? You get more diverging pathways. Like a one-step reaction, you're probably going to go from one stereoisomer to another stereoisomer, and that's going to be it. One product, very clear. Here, we get to this secondary cation. Like I said, we can do elimination, we can do rearrangement, and in fact, I haven't shown it, but it doesn't just have to be a methyl that moves. This carbon could move, and you could get a 5-membered ring. Probably see some of that. And every one of those cations can then do substitution or elimination. And then if your product, if one of the products can be 2 different diastereomers, probably will be. The cation's flat, it'll always give you a racemic product, even if you start out with only one enantiomer. So SN1 and E1 reactions tend to be quite messy. Like if I need to go up in the lab and do a substitution reaction, I would much rather do an SN2 than an SN1 if I can get away with it. Like I said, that's a little down in the weeds. If I just ask you to predict a product, like I said, if I give you this reaction and no more data than this, and you draw me this, I'm happy with it. Like you don't have to tell me all 12 products that come up. But you might get a question that's more like a word problem, right? Like, some dude came in and he mixed up chemicals and he got 14 compounds, provide a mechanism. If you see specificity, pure stereoisomer, one product, that's much more likely to be an E2 or an SN2. If you see a whole bunch of products, no stereoselectivity, it's way more likely to be SN1 or E1. Yeah? Yes. So the bond breaks heterolytically. Chlorine's more electronegative, so it takes the electrons, leaves the carbon positive. Right, I haven't gone all the way, I haven't gone, yeah. I'm taking my time. I'm relishing this mechanism. Yeah.
How do you, this, we can answer this after this, but how do you differentiate like an E2 from S2?
Well, yeah, we'll do that. I mean, the flowchart does it. I really should have just handed out the flowchart and we all go get pizza or something. But you're paying me to do more than that, so I will. Yeah, so let's finish this mechanism, all right? So we get to this tertiary cation, and now how do we get from the tertiary cation to the, let's say, the elimination product, okay? So what do we have in here? So we're going to have chloride minus, and we've got H2O. This is now a messy board all of a sudden. All right, so if you look from here, when you go through these mechanisms, you always want to see what has to happen between two structures. Like if I know A turns into B, maybe I don't know how many steps there are, but I want to just take stock of what bonds break, what bonds form, and then can I do that in one step or more? And so here, to go from this tertiary cation to the elimination product, right, I need to make a double bond here, so the kind of the higher alkene carbon has already in the tertiary cation all the stuff it needs. It's got a methyl, the CH2, and the carbon with another carbon with a methyl. Right? The right-hand alkene carbon has a methyl. It doesn't have a hydrogen, so we've got to get rid of that hydrogen. The easiest way to get rid of hydrogens, again, this is kind of prelude to future chemistry. You're not guaranteed that when you lose a hydrogen, you're not guaranteed that it comes off as an H+. In Orgo 1, you are, right? If we're going to lose that hydrogen, it's coming off as an H+. It's going to be an acid-base reaction. And honestly, that's the way to bet at any stage of your chemistry life. All right, if a hydrogen comes off of an atom, it probably comes off as an H+. There are times it doesn't. It can come off as an H dot. It can come off as an H minus. But overwhelmingly, it's going to come off as an H. So we need a base to take this proton. And then you asked where the electrons come from. The electrons come from this CH bond. Okay, so the mechanism here, we've got chloride as a base, water as a base. Water is also the solvent. There's a whole lot of water. Water is also a stronger base than chloride. Okay, so if we have a whole bunch of water, one chloride, even if we just had 1 to 1, if there's one water and one chloride, we'd expect water to take the proton. But there's actually like probably 100,000 waters per chloride. So the water is going to take the H, and then those CH electrons form the pi bond. Okay, so the arrows start with the oxygen on water, the lone pair on oxygen. They go to the H. That makes an OH bond. And then the second arrow starts with the CH electrons. It doesn't start with the H. It starts with the CH electrons, and it goes in between the two carbons. It makes a pi bond. All right, so with this one, we also get H3O+. Okay. So draw a mechanism for that. All right, so this is the same tertiary cation as up here, and that's going to give us the cation. Okay, so we have to make a CO bond, right? And the O is going to end up bonded to the carbon. Actually, you can't really tell which carbon is positive and which isn't. Like I've drawn it suggestively, but you can flip it over, you could move that H. And in fact, this H probably moves back and forth. Remember I said that's an equilibrium process. So from the tertiary cation here, if this H moves over here, I get a tertiary cation. I actually get the same tertiary cation. So that'd be 50-50. If we somehow could go in and say, make this compound where only that carbon was a C13 and that carbon was a C12, once we do the reaction, we'd find the OH is 50% of the time on the C13 and 50% of the time on the C12. All right, so how many people then, you don't have to raise your hand or otherwise say this. I just want you to look at your mechanism. How many people for this step have drawn a hydroxide, an OH minus? If you have, you're wrong. All right, so I see that a lot. I'm not trying to put the thought into your head. But it's real. I mean, I think this maybe happens more on an exam where you get rushed and you're a little stressed. And you look at this, like I got a carbocation there and I need to put an OH on it. I'll just have hydroxide hit that thing. All right, and if hydroxide makes a bond to that OH, I'm done. And that's kind of what you want to be on an exam, right? I want to be done with this problem. Okay, but that doesn't happen, and the reason it doesn't happen is sort of technical, but a carbocation is a really strong Lewis acid. It's very electron poor. Hydroxide is a strong base. Again, you're not going to have reactions where the only way to have a strong acid and base in the same reaction is if you pour them together. All right, you're not going to have a reaction condition that over here is making a strong acid somehow, and over here is making a strong base. All right, so you can take sulfuric acid and hydroxide and you can pour them together. It splatters and you get a lot of heat. In a reaction, reactions are either going to tend to form acids or they're going to form bases. Here, right, so the leaving group leaves, that gives us a strong acid. So at this point, the reaction's under acidic conditions. It's kind of hard to see because probably most of you at this point are not thinking about cations as acids, but they are. And you can see that here, right, this carbocation gives up an H+. So it's an acid. All right, so water is going to attack. It's another, I don't know, well, I do know where this came from. If you want to talk about etymology of words. Organic chemistry, this chapter especially, but in general, we tend to use the word attack. If two molecules add together, that's not just nature trying to find like a low energy path to stabilization. One molecule attacks the other one. That's the way people describe it. All right, so it's not like violent, but this oxygen with electrons, the word we use is attack. We'll make a bond to that carbocation. Now all the atoms are going to have a full octet, but the charge has to still be there. And so this will give I know I'm writing small, sorry. All right, water attacks the cation, not hydroxide. So neutral water, which is a weak base, but a weak base can react with a strong acid just fine. So water comes in, makes a bond to that carbocation, but the two hydrogens on the water stay there for the moment. All right, so the arrow is from the electrons on O to the positive C, and that's it. There are no other arrows. The intermediate product has the alcohol protonated, right? It's just got water bonded to that carbon. And now that's going to be a strong acid. So if you have a proton on an oxygen with 3 bonds and a positive charge, that hydrogen is really acidic. And so again, now we just have water, another water, can't write 2 all of a sudden, another water will take that acidic proton, that gives us our product, and H3O+. Again, I can't emphasize this enough. You have a lot of water here. All right? Anytime anytime you do a reaction in a solvent, so you guys are doing a reaction this week in lab. You did one before the break, right? Pay attention to what you're using. You've got DMF. You're pouring like 6 mils of DMF. And DMF's this tiny little molecule, so you've got a lot of molecules of it. All right. There's a term here you should know. You'll see it in the book. I mean, it's not like I'm going to ask you to fill in the blank or anything. Any reaction where the solvent is also a reagent. So in this reaction, water both reacts and is the solvent. So anytime you have that situation where the solvent also reacts, it's called a solvolysis reaction. And the solvolysis product is this rearranged alcohol. So this is going to be an SN1 reaction, and this is going to be an E1 reaction. The eliminations always give an alkene. Substitutions always swap out. Some group comes in and swaps out for the leaving group. It's a multi-step reaction, and the slow step for both of these, the slow rate-determining step for both reactions is the leaving group leaving. And so the rate is only dependent on the concentration of the alkyl chloride at the beginning. Yep. Yeah. So, yeah, it's a really good question, and it's a really good question, and it's a long conversation. Well, I'm going to give you a short answer, but you just some of it you just have to take. All right, so these charges on here, and this is true. Like if you think about the carbon chloride bond here, right, if you just think about the polarity of the carbon chloride bond, the chloride's partial minus, the carbon is partial positive. They're both neutral though. The formal charge on both atoms is neutral. And so here's the thing. Formal charge, the reason we say formal and not just charge, I mean, I guess I do, right? I often do this. That carbon's positive, that oxygen's positive. Those are formal charges. And the reason we have to use the word formal there is they don't always correspond to reality. So formal charges are basically a bookkeeping way of keeping track of is there charge in the molecule. Now, it works really well for the carbons here, right? So in the secondary and tertiary cations, those positive charges show a carbon that doesn't have a full octet. That carbon is really electron deficient, which you would think is the definition of positive, right? For this oxygen, let me draw that a little better. It's not well drawn. All right, so there's this intermediate. If you weren't seeing it clearly, that's this intermediate alcohol. You can think of it as an alkylated water, protonated alcohol. All right, so the formal positive charge is on this oxygen. I'm even going to put the other lone pair in. That oxygen has a full octet. Right? It's either got on its own or sharing 8 electrons. So it's not that electron deficient. It would rather, I mean, bookkeeping-wise, it would rather have 2 bonds and 2 lone pairs. But if I then asked you to draw what's the bond polarities, so this is the thing that kind of creeps people out sometimes. All right, if you think about the polarity of those bonds, it's still the same. The oxygen has got, if I just think about the 2 electrons in the bond, those electrons are more on the oxygen than they are the other thing. And now because the oxygen is just a little bit, it's not electron deficient, but it's overextended, right? If we use electrons and money, my electron and money analogy, that oxygen is now a little overextended. It's promised a loan to too many friends. All right, so it makes it actually a little more electronegative. That oxygen is now pulling electrons, right? It had been sharing 2 electrons here with the H and was happy to do so. Oxygen's like, yeah, I got electrons, we can share. But now it's like, oh crap, I got to give the carbon some electrons. And so that actually makes the partial positive charge on the 3 things bonded to that oxygen are stronger partial positives than they normally would be. Okay, we had this on the exam. We compared, or I asked you to compare, this might not be the exact. I asked you to compare which one of those is more acidic. Right? And there was a pretty big deduction if you screwed those 2 up. There was a nitrogen analog as well. There was a neutral N and a positive N. Okay, so again, partial positive, partial negative. That carbon is partial positive. Over here, right, you're used to seeing that. That O plus, any one of those 3 bonds to the O plus is a more polarized bond than in the neutral OH. All right, so if we just look at the OH, this OH bond is way more polar than this OH bond. And that OH bond is quite polar. Right, because that oxygen is basically, the formally positive oxygen is saying, look, I want a lone pair. So it's kind of saying to all 3 of the atoms it's bonded to, give me those electrons back. And so, like I said, this is, I think, first time I saw this done, that's a crazy formalism right there, right? I've drawn a positive next to the O, and then I've said, oh yeah, it's also partial negative. So it's partial negative in terms of the polarity of its bond with any of those 3 things. The formal charge is basically just saying this molecule has a positive charge distributed somewhere. All right? It works out that, like always, the positive charge is going to be distributed on the less electronegative atoms. So that's why H3O plus is quite, the O is positive, formally positive in H3O plus, but when H3O plus reacts with a base, the base grabs an H, not the O. It's kind of a long answer. Is that okay? All right. So the take home from 40 minutes of class here is basically if there's no strong base or good nucleophile here, the leaving group leaving is going to drive the reaction, and that's going to usually be pretty slow. Right? That chloride, this molecule is quite stable. You can put it in a bottle, put it away, it'll stay there. But if you give it a chance to react, like really what happens is we get this equilibrium established. There's not much of the secondary cation. But if you give it a little bit of heat, maybe it rearranges. And then you need a base to react with it. Okay? So SN1 and E1 tend to be slower than SN2 and E2. Which is why if you look at that, if SN2 and E2 is possible, that's what you're going to see. All right, let me collect my thoughts. All right, so I've given you a printout of this. Folks at home, again, here's the flow chart, substitution, elimination, PPTX on module chapter 7. You should open that up. I said this during the spectroscopy phase of the class, and I've said this to my lab students. It's a good idea to write stuff down. We all, as technology has progressed and we've been more conscious of environmental impact of paper and stuff, we tend to use less of it. I like that. There's a part of me that really likes that. On the other hand, computer screens, if you have one screen, are really bad about seeing large sets of data. Right? So if in your dorm room you've got your laptop and maybe 2 screens you're plugged into, you can do this. You can do proton there, carbon here, mass spec here, and you can sort of see it all at the same time. Or you could put this flow chart up on one screen and look at the problem over here. Now, obviously on exam 3, maybe not obviously, but I'll tell you, on exam 3, you will not have access to this piece of paper except in your mind. All right? And I don't want you just to look at this and memorize it. That's hard to do. I want you to think logically through it. But for right now, I would use that as you try to answer questions. So there's a reaction. What I'd like to know is, what is the product of this reaction? And by which mechanism does it happen? So here, I'm not asking you necessarily to draw a mechanism. I'm asking you, is it SN1, SN2, E1, E2, rearrangement, neither? And use the flow chart, all right? So again, you're going to start in the upper left and sort of work your way around it. I'll give you a couple of minutes head start, and then I'll catch up to you. If you get the first one I did and want to try the other two, feel free. Okay, so like I said, first time through this, there's a lot of pathways. It flows. There's a lot of stuff to think about. I'm not suggesting this is easy to keep track. And I just want to re-emphasize, this is a way to make a prediction about a reaction. And any time where you're sort of like, it could be a couple of things, the flow chart may say, well, that means this is favored or that's favored. But in reality, you got to do the experiment. So, okay. So do we have a leaving group? Yes, there's a bromide. So again, the leaving groups are going to be chloride, bromide, iodide, and then just start a tab here of stuff we have. And actually, in terms of how good the leaving group is, like how easily does that group leave, and really what this is saying is, how strong is the bond between an sp3 carbon and this group? The bond is weakest with an iodide or this sulfonate ester. And this is often going to be called O-tosylate. This is probably the one I'll use. You'll also see mesolates. It's just a negative, or it's an O bonded to an SO2, and then that SO2 is bonded to some sort of R group. So these are better leaving groups than bromide, and that's a better leaving group than chloride. All right, so yeah, you got a leaving group. So there you go. To the right, we can do substitution, we can do elimination. Are there beta hydrogens to the leaving group? Yeah, there's 8 of them actually. 2 here, 3 there, 3 there. So we can do elimination. All right, so we can do elimination and substitution. Now, is there either a strong base or a good nucleophile? Less confident looks at me. Some shakes of the head, but all right. So again, this is a big see class notes and text to determine the reactivity of the Lewis base. All right. So this is a point where there's often a lot of confusion. Hopefully you can identify a strong base from our work in chapter 3 and 6 and on the last exam. The thing I would like you to come back to is hydroxide and ammonia. All right, so hydroxide and ammonia are strong bases. Weak and strong in any respect, it's always a comparative thing. Fast, slow, weak, strong. All right, like am I strong? This could get personal. I'm big. You guys should charitably say, yes, Dr. Jones, you're strong. You're a big, strong man. Falling apart, but okay. When you say that, really what you're saying, if you just say a person is strong, you're saying a person is strong relative to an average person, right? Like that would be the comparison. And maybe I am. I'm bigger than average, so hopefully I'm stronger than average. Am I stronger than a bear? No, definitely not, right? So if we're comparing to bears, I am weak. If we're comparing to like gnats, I'm super gnat. I don't know where I'm going with that. All right. Weak and strong is always a relative thing. So if you just say, is it a strong base, you've got to have some like definition in mind. For the reactions in this chapter, basically hydroxide and ammonia, that's the line. If you're a stronger base than hydroxide, or if you're as strong as ammonia or as strong as hydroxide, you're a strong base. Okay, so this is then going to get us things that are like, all right, so methylamine, trimethylamine, anything with a localized negative charge on O, right? If hydroxide's a strong base, then any kind of localized negative oxygen is probably going to be a strong base. there's also something in here about, do I have it up? Sometimes I do. Yeah, so the pKa of the conjugate acid, you have to maybe know some pKa's in there somewhere. But hydroxide and ammonia are basically your cutoff. So I'm going to tell you that there is a strong base in this reaction. What is it? The what? That's bonded to the sodium. Yeah. So you've got two choices here. There's no strong base here, right? Nothing with a negative charge. The only thing with electrons is the bromide. So now you've got a choice here. And again, this is a point where you've got to read these structures right. So all the, well, not hydrogen, but from lithium down in the alkali metals, lithium, sodium, potassium, cesium, rubidium, and actually the group 2 as well. If you see those in a molecular structure, you assume they're cations. All right? If I see a lithium in a formula like that, or I guess here a sodium, if I see a sodium, that is a sodium plus 1, which means what it's with is minus. All right? So this sodium is plus. That means that O is minus. So the OCH3 minus is your strong base. The methanol is not. And I mean, this makes it, I understand why this can screw some folks up. That's the Lewis structure. Let's put the whole thing in there. This is the Lewis structure of methanol, CH3OH. So methanol, if you write it like that, CH3OH, it's got an OH in there. And again, you guys have sort of been conditioned, right? OH is hydroxide. That's a strong base. That OH is not hydroxide. It's an alcohol. It's a neutral oxygen. So this is your base. And it is a strong base. Right? Because it's in line with hydroxide. Hydroxide's a localized O minus, methoxide, localized O minus. Is it a good nucleophile? All right, so here we haven't really talked about this. What is a good nucleophile? This is a bit of a circular definition. I'll show you, I'll draw some structures to illustrate it here in a second. Any strong base is going to be a good nucleophile unless it is too big to do that. So there are 4 bases: hydroxide, methoxide, ethoxide, and T-butoxide. In terms of base strength, they're all right around the same level, okay? A localized O minus. Actually, the T-butoxide is a little strong. It's a bit stronger of a base. Hydroxide's the weakest base, but it's like an order of magnitude. It's not that much. But down here at the bottom, T-butoxide is a poor nucleophile. Hydroxide is a great nucleophile. And it all comes down to steric bulk. So remember what the nucleophile's got to do. The nucleophile, all of these are Lewis bases. In the in the SN2 and the E2 reactions, the Lewis base, or the thing with electrons, either the base or the nucleophile, is an electron donor. There's a lone pair on on an atom, and that lone pair has to access another atom. Now, if it accesses a hydrogen, hydrogens are always on the outside of the molecule. Right? Hydrogens are always on the surface. The carbon, if we want the nucleophile to attack the carbon, that lone pair on the nucleophile has to get close to the carbon. Remember, the curved arrows are really good. Once you get these down, like, you can think about reactions really well with them. They're deceptive in that it makes it look like molecules can react from, like, across the flask. Like, I'm a water hanging out over here, there's an alkyl chloride over there, and I'll just throw some electrons over there and make a bond. Anytime, this arrow is actually saying that the nucleophile here would have to get within a bond length of that carbon. Okay, so it has to get in really close. The more steric bulk, and by sterics I just mean sort of other atoms, the more other molecule bits that are hanging around the atom with the electrons and the atom that wants the electrons, the slower that process is. Right? So, right, if this nucleophile wants to make a bond there, if this nucleophile is really bulky, and here, right, that carbon's got all this crap around it, it's going to be really slow. Whereas, if this molecule wants to make a bond to the H is by definition on the outside of the molecule. H's make one bond. So there's, like, H's are always accessible. Okay, so any strong base is going to be a good nucleophile. It's going to become a worse nucleophile the larger it is. The more steric bulk around the basic atom, the worse the molecule is as a nucleophile. All right, that would be easy enough where we could stop there. I'm going to erase this, and I'm going to give you a list. I think that's about it. There are quite a few molecules that are good nucleophiles without being a real strong base. I'll let you write stuff down for a minute. All right, so again, if you're thinking about what a nucleophile does, it's giving electrons away. So that's sort of the definition of a strong base. That's why a strong base is a good nucleophile, right? A strong base is a molecule or an ion that gives away electrons really easily. So by definition, if something is a strong base, it's probably going to be a good nucleophile. And there's just this steric question, right? It's not that T-butoxide is not good at giving electrons away. It's just physically prohibited from reaching the carbon it wants to give electrons to. There are some molecules, and this is especially true as you go down the periodic table. So any sulfur is more nucleophilic than an oxygen, because the electrons it wants to give away, the valence electrons it wants to give away, are farther from the nucleus. Right? So the atom is said to be more polarizable. Right? This sulfur is chugging along. Over here is a positive atom. The positive atom attracts the electrons in the sulfur. And it can do that easier than it can the electrons in an oxygen, because the oxygen electrons are closer to the nucleus. So sulfurs, and even neutral sulfurs, are pretty decent nucleophiles. A negative sulfur is a really good nucleophile. It's not a particularly strong base, though. And this gets into, it's actually a pretty complicated question between does an atom want to give electrons to a hydrogen versus a carbon? And there's a bunch of theories from that. For right now, just sort of put those 5 structures in your head. Those are good nucleophiles. Cyanide, azide, carboxylate ions, so the conjugate base of a carboxylic acid, sulfurs, and phosphoruses. All right, so when you look at this, you get to this this is the big branch point, all right? Is there either a strong base or a good nucleophile present? So here we've decided we got a strong base. That's all you have to decide at that question. The answer is yes, so you go to the left. It turns out methoxide is also, in addition to being a strong base, is a pretty good nucleophile. Very good nucleophile. All right, so what that means I'll explain this. This is not a well thought out sentence. All right. If you have a strong base or a good nucleophile, you have conditions where an SN2 or an E2 can happen. Right? Remember, SN2 and E2, I haven't done one of those mechanisms yet today. Those are the one-step reaction. Nucleophile comes in, bang, kicks out the leaving group in one step. You invert the stereochemistry on the carbon. That's the only product. The rate law is bimolecular, hence the 2 in the name. SN2 and E2 reactions are driven by the base. So if you have a strong base or a good nucleophile, you can do an SN2 or an E2. If you don't have them, if you have a weak nucleophile, weak base, you're more likely to see SN1 or E1. So if SN2 or E2 are possible, SN2 and E2 are faster reactions, again, generally, than E1 and SN1. Because they're faster, so that means if you've concluded that, yeah, I got a strong base here, you're going to see E2 or SN2. Okay? So we went to the left. Now, is the leaving group on a tertiary carbon? It is. Okay, so this, and I already did this. So now we have OCH3 here. This is our nucleophile. The SN2 would require that OCH3 minus, it would require specifically that oxygen to make a bond to the carbon. But again, the carbon, bromide, right? So the carbon bromide, the electrons have to go into the sigma antibonding orbital. That requires that the nucleophile come from directly opposite the bromide. All right, so if you didn't see this in the Tuesday lecture, you should go back and look at that. In an SN2 reaction, the nucleophile has to attack the electrophilic carbon from the backside. Okay? So it's got to come from directly opposite the leaving group. Nucleophile comes in, bonds to the carbon as the leaving group leaves. But the backside of this carbon is protected by this butyl group, pentyl group, and 2 methyls. There's a lot of mass there. And so the nucleophile can't get in there to do that. With a tertiary carbon, the more steric hindrance there is around the electrophilic carbon, the slower SN2 is. For a tertiary carbon, it's 0. SN2 reactions do not happen on tertiary carbons. They're pretty slow on a secondary carbon. I've tried to do this, it always pisses me off. Secondary carbons are the ones that are sort of in between for all these. They don't make a good cation, they make an okay cation. So SN1 and E1 is kind of slow. It's hard to do a nucleophilic attack on them because SN2 is slow. So you can do E2 pretty easily, but all the others are slow. All right, so here the nucleophile is blocked from getting in there. cluttered up my board. All right, that's blocked. So instead, what happens is an E2. And then, like I said, that hydrogen is on the outside of the molecule, so it's much more accessible. It's like picking a hair off somebody's head instead of punching them in the gut. Like I said, attack. This gets lots of violent imagery. Most of this was done sort of first half of the 20th century to the middle of the century. We're all fighting world wars, a bunch of macho guys in the labs. Okay, so attack is the imagery, and like I said, I'm sorry I'm using that analogy, but like, it would be easier for you to like come up behind me and grab a hair off my head, not recommending you do that, than to like stand in front of me and punch me in the gut. I'm definitely not recommending you do that. I'm 50, I'm slow, like, okay. So these are real, I guess what I'm trying to drive at there is these are real physical objects having to interact with each other. They're not abstract ideas. All right, that negative O, if it's going to take an H, it has to make contact with the H. If it's going to make a bond to the C, it's got to make contact with the C. The H is way easier to make contact with. So the reaction we get is an E2. This is a concerted process. The methoxide grabs the H, the CH electrons make a double bond. That kicks out the bromide. And so our product is that. Plus, if you want to draw it, CH3OH, we get methanol, and we get a Br, and that's going to be associated with sodium, so we get a sodium Br, basically. And this is irreversible. All right, the E1 reaction is reversible. Leaving group leaves, you end up making H3O plus in the leaving group, or H in the leaving group. In the E2, we go from methoxide to methanol. Strong base to a weak acid. So this is way downhill in energy overall. So like I said, the reaction is driven, the E2 and the SN2 are driven by the base and the nucleophile. Whew. It's a lot of stuff. Six minutes. Yeah.
So with 25 Celsius, you consider it high temperature?
So you'll notice I put the temperature on all these. Yeah, we talked about, this is one of those where I'm like, we talked about this, but we did it last time. So you may not have seen it. Again, temperature is always a relative thing. In general, elimination is favored over substitution at higher temperatures. As the temperature goes up, you're more likely to see elimination. In this problem, that is useless information to you. All right? This reaction can only do E2. With a strong base present, the E2 is going to happen way faster than the leaving group just leaving. So you're not going to see E1 or SN1. And because the leaving group's on a tertiary carbon, you can't do SN2 at all. All right? So if it was a secondary carbon and there was a question of, hey, I could do SN2, I could do E2, at a lower temperature, you'd think SN2 would be favored. At a higher temperature, you'd think E2 would be favored. Your question, no, 25 is not a high temperature. And again, a high temperature depends entirely on your point. The point of view here would be the molecules. Like, does this particular set of reagents do elimination at a high temperature or a low temperature? I have done E2s at 0. All right, the reagents are just set up where the elimination's a lot faster. And I've done SN2s at 100 degrees. So it's always kind of a give and take. What I tell you, because asking you to guess that, I don't let you go up and do experiments in the lab during the exam. Like, that would probably help things. Make it a long exam, but all right, so 50 degrees is what so if it's above 50, I'm thinking elimination is preferred. If it's below 50, I'm thinking substitution. And I probably won't, like, I'm not going to say like 51. And really, truly, if you go in the lab and you want to do this, like if you want you're never going to want both products. Like, you want one product. If I want the alkene, if I want elimination, I do the reaction as hot as I can. Like here, well, substitution's not a possibility here, but if you have a reaction that could do SN2 or E2 and you want E2, you use the bulkiest, strongest base you can find, like something that's going to drive the reaction really hard but not be able to be a nucleophile, and you heat the piss out of it. All right? If I want substitution, then I use something smaller. If what I want works with it, I choose one of those good nucleophiles that's not a strong base, and I do the reaction as cold as temperature. So I'm going to leave it there. Do these two next. Folks at home, folks in class, these will be the first two we talk about. Use the flow chart. Dive into Wiley Plus. You can start doing Chapter 7 problems. Look at the final project. I haven't mentioned that today, I don't think. The final project is assigned. It's 150 points. Open note, open book. You can talk to each other. Don't copy. I mean, in large part, oh, that reminds me. I'm supposed to tell you something. In large part, there is no way for me to judge this, right? If one of you does this assignment this week and then, takes $100 a head, I will never know. Don't say that would be smart. That would not be smart. That would be a violation of the Wake Forest Honor Code. And if I can find out, let me tell you how I'll find out. So if you do it all right, I will never know. But if you draw, this happened once. If you draw a molecule that's got a carbon with 7 bonds, and 2 of you turn in exactly that molecule, there's a very high chance that that was cheated. So don't cheat. Do your own work. Like I said, you're going to take Orgo 2. Well, that is the next thing. Again, if you need to go, you can. Some advising. The schedule, I think, goes live tomorrow. So the next class for you guys to take is 223 and 223 lab. You don't actually have to take them together the way you did 122. I would recommend it if you can, but if it turns out taking 223, you have to take the lecture first. But if you can't fit a lab in somehow, I don't know when the labs are, but if you can't fit a lab in, you could separate those two. Also, I think they're offered in the summer. Yeah, and also Dr. Amanda Jones is offering 223 in the UK in the summer of 22. That's a long time to wait. Probably not ideal for you, but it is there. We've been asked to remind you about the honor code. We've been kind of relaxed about it with online stuff and COVID pressures, but we're all here. It's really not a huge concern of mine. I give live exams. So as you're working the final, my big incentive to not cheat on the final project is that is designed to help you prepare for the final exam, right? Exam 3 is May 4th. The final exam is scheduled for May 8th. You do not have a lot of time to go back and go through exam 1 and 2 material. The final project will hopefully refresh all that stuff for you. Yeah. Sorry? Yeah, there's a joke in there somewhere. They're longer, more complicated problems. It's not super long, but if you put it off until the night before it's due, you won't finish it, or you won't finish it well. So I don't want to encourage cheating, but I also don't want to discourage you guys from talking to each other about it. Okay? If you have a question, and I don't even mean generalities, like what the hell is going on here? Feel free to talk to each other about it. Just don't go to your friend and be like, let me see your page. Or never mind. I won't tell you all the different ways. I know how to game this system, all right? It's my system. Do the work, because like I said, the final exam will be sort of a third exam 1, a third exam 2, and a third exam 3. You're going to need to review the exam 1 and 2 stuff, but you're not going to have a lot of time for it. So do the final project honestly, and it will prepare you. But still, it's open note, open book. You can talk to each other. It's 150 points. If you're looking for curve in my class, that's where it is, okay? You really, all of you, if you give it enough time and effort, should score in the 140s probably. So that is a lot of points. All right, it's Thursday, right? have a good weekend. I'll see some of you on Tuesday. I've got office hours. Come by if you want. Yeah. Ciao.
Can I ask about something on the board?
Mm-hmm.
I understand the mechanism that we just went over, or the idea that this is an E2 reaction, and I understand how it occurs.
Mm-hmm.
But the drawn out product, I don't know.
Did I count carbons wrong?
No. I'm asking the.
Thanks.
Why would it be like? Like why couldn't it be just drawn like that as well?
Well, you got to have a double bond in.
Yep.
Well, because that's sp2 trigonal planar. You've drawn that as 180.
Okay.
You've got everything connected right, but it's just not.
It's not
It's not pretty.
cool. Okay.
So,
That problem, why wouldn't it be SN1? Is there no product solvent that way? Or like?
it is a product solvent. SN1 is slower than E2.
Okay.
So yeah, like bromide leaving and making a tertiary cation is pretty good, and then you could have methoxide or methanol come in there. Practically, the bromide leaving is a lot slower than methoxide grabbing an H, right? So you got to break. You got to have a neutral, decently strong bond just spontaneously break versus a strong base grabbing a proton.
But like if you do this in the lab, you'd have some SN1.
You could ease it. Then what it probably depends on is the concentration of methoxide. So you know when I say like this is the slow step, well actually it's not even slow step there. The rate of bromide leaving is pretty constant. But the rate of the proton abstraction, the E2 is bimolecular. So if I keep cutting the concentration of methoxide, sooner or later then SN1 gets competitive with it. Like I said, when you set up a reaction, you want one thing to happen. So what you do here is you do this concentrated, and you wouldn't do this at 25. I mean, you
That's
have,
why
like if I was really doing this, this would be like with like 12 equivalents of methoxide at 6 molar at 100 degrees. Like, I'm not giving this guy a chance to do an SN1. So you could certainly set it up in such a way that SN1 happens, but you would try not to do that.
That helps. Thank you.
Yeah.
I was wondering, so what kind of like conditions do we need to worry about, like the carbocation rearrangement?
At least one of those.
So it's like whenever you see a ring, just
No, not necessarily a ring. I mean, yeah, so that iodide there, yeah, like if the iodide leaves, you get a resonance stabilized cation. The key thing there is though, like in that step, there's no strong base or good nucleophile. So the way I teach, and again, you can always find conditions. Like I'm not teaching Newtonian physics here, right? Like you can find conditions where, it looks like E2 ought to happen, but it's really SN1. If I had sodium methoxide in there instead of just ethanol, then I'd be looking for SN2 or E2. Yeah.
I just had a quick question about Wiley Plus.
Uh-huh.
So is it just for practice, or like, I was just a bit confused.
Have you been doing any of it?
I've been doing some.
Yeah, you're going to be, in terms of the points, you're going to be fine.
Okay.
It is mostly for, I put enough points in there to try to get you guys, like if you didn't want to practice, you'd be like, oh, I want those points. It is for practice.
Okay.
And the farther you go into it, the worse it is. Like it's really bad about mechanism. Anything where it's asking what the mechanism is, like it was done by a computer programmer, not an organic chemist. So it's like the arrow has to be like on this track right here. An organic chemist, it could be straight over here, it could be curly-cued, and it doesn't let you do that. So it is only for practice and feedback.
Okay.
Because even though I'm now doing office hours in person, like we're still like I just can't meet with people. Chem Center's not open, so I normally don't require it, but it gives you some feedback. So and if you find you're struggling with something that it's not explaining well, just come see me.
Okay, sweet.
Yep.
You have a good weekend.
You too.
Hi, so I was looking at the syllabus and it says the final is optional. Is that still the case or was that just last year? Because
No. If you are happy with your score on exam 1, 2, and 3, if you take all 3 exams,
right, and then it averages.
and let's say your average on exams 1 through 3 is 84, and you're like, I can't do better than that on a final. I'm not saying that's
Right.
you can.
Yeah, exactly.
No. I don't know if you've been kind of if you feel like a lot of times it depends if you've done an 84 every time.
Right.
You're probably an 84, right? That's probably where you know it.
Right.
If you made a 60 and then an 80 and then a 90, like you're getting better and you're improving. I would, like if I had one low score like that,
Okay.
I wouldn't take it. And also the final then replaces No, the final didn't replace anything. Sorry. If you like your score on those 3 exams, you can not
But
take
once
the final.
if you decide to take the final,
If you come in and sit down and take the final, it counts.
whatever it is, it counts.
Yeah.
Okay,
Yeah.
thank you.
So yeah, if you come in and you're like, oh crap,
Yeah.
this is really hard. Yeah. And there's like no way to win here for me.
Right.
So I did that sort of like a lot of people are like, I'm worried I'm going to bomb the final.
Yeah.
And I'm like, oh, well, here, you can relax. Like, but you can't, I don't know. Like then there's a lot of stress in just figuring out, like if you have a 60, there's no stress, you take it. If you have a 98, there's no stress, like you take your score.
So far, I've been relatively in the same place, so
Yeah.
I feel like if that continues.
And is it higher? And the other thing I will, after exam 3, come talk to me and I'll tell you like where you stand.
Okay.
Like I can't tell you what your grade will be, but I can give you plus minus what your grade will be.
Perfect. Thank you
Yeah,
so much.
you bet.
I just, I honestly know what to tell you, but how's your day going and stuff?
It's going all right.